All right, so let's go ahead and start. We're gonna continue from the BitTorrent lecture yesterday because we had a slight glitches yesterday in the streaming session. So what we were talking about is the BitTorrent system. We were talking about in BitTorrent, the clients or the peers come and go. Therefore, you get these churns. So maybe in the middle of the transmission, in the middle of downloading file chunks from another peer, you get interrupted. Okay, that is actually very likely to happen. Also, when a peer, such as yourself, finish downloading a file, chances are so high that you decide, hey, I got my file. I'll just leave it. If that is the case, you get also a whole bunch of these chunks suddenly disappearing. All right. Only very few users will stay on for a little while to allow other peers to download chunks from you. So churns is indeed an issue, one of the major issues in P2P network. Now, let's move on and continue hearing the rest of the BitTorrent, how we divide the chunks, how we download chunks, selecting chunks to download, and who I choose to upload first, okay, because there are so many peers demanding chunks. I'm sure that there are many people in line asking for chunks from you, but who do you upload first? Okay, so these are subtle designs in BitTorrent. The part that Polly finds the most interesting about BitTorrent is this. The strategy to request chunks and the strategy to send chunks. Let's talk more about the requesting strategy first. The setting is this. Given a file that many of the peers are looking for, so they'll be downloading chunks for the file. At any given point in time, because they're doing the downloading independently and they might be connecting to different neighbors, they might not know each other. So at any given point in time, different peers might hold a different subset of the chunks belonging to the file. All right? And the way it progresses is each peer then will periodically query the neighboring peers. So asking neighbor 1, neighbor 2, and neighbor 3 for the set of chunks neighbor 1 has for that file, neighbor 2 has for the file, and the set of chunks neighbor 3 has for the file. Okay? So it's kind of an inventory check. Now, once the peer receives all these inventory check reports, the peer begins to count which chunk is the rarest in the P2P network. All right? And the peer begins to download from the rarest that he does not quite yet download yet. So that is the requesting strategy. Now, if you think a little bit more about it, why rarest first? If I tell you, look back the previous slide, the issues we might run into are these, right? A peer might come and go, right? So as they move from one subnet to another subnet, it might get disconnected, the IP addresses might get changed. If it's in the middle of the download, those chunks will disappear from the P2P network. Also, right, when some peer finish downloading all the chunks for a file, and if the peer is selfish, they might just leave the network entirely. So in a P2P network, real users will all have this anxiety of not being able to find a specific chunk for a file. And that is also when BitTorrent downloading can go really, really long. It's not because there's not enough capacity, but it's more. Yeah, certain chunks are no longer there on the network. Okay, so it's actually quite important this rarest strategy is implemented on a P2P network like this. And another aspect that's interesting is the sending strategy. And I love the name, tit-for-tat. It sounded kind of fun. Right? The way it works is also very simple. Alice here is an example peer. She will send chunks to others that are sending back to her at the highest rates. Okay? So, hey, if you're generous to me, then I will be generous to you. Okay? Eye for eye, tit for tat. But this simple strategy might create this problem. Other peers are not sending at the highest rate, will be choked, then these guys might not get a chance of downloading certain chunks from Alice at all. Right? This is actually not quite that good. So Alice will reevaluate, okay, the top 4 every 10 seconds. So those peers who discover that they're choked, they're not downloading any chunks, they might decide to contribute more uplink capacity. Therefore, as a result, they might get some chunks from Alice back the next round, the next 10 seconds. Okay, so this is the general strategy. Okay, share your uplink bandwidth, then I share mine. But this might not be a good thing either, because some of these peers might be very non-resourceful, meaning they have very, very low uplink capacity. As a result, they might always come up short here in the competition for the highest rate neighbors. So every 30 seconds, Alice will be very generous, okay? And not look at the sending rate coming from the neighbors, but just randomly pick one of them and start sending chunks to them. Right? So optimistically unchoke, okay, a particular peer. Now the newly chosen peer will join the top 4 and receive chunks from Alice. Right? But this is done at the lower frequency, only every 30 seconds. Right? So mostly favoring those who are contributing more bandwidth for uplink purpose, but every now and then, not bias on the uplink capacity of the peers and openly share. Okay, interesting, isn't it? And let me animate tit-for-tat here. So Alice here optimistically unchokes Bob. So Bob could be a newcomer into the network. Okay, Alice might randomly discover, okay, there's this guy Bob there. Alice begins to send chunks to Bob. And Bob there says, wow, thank you for all the bandwidth, all the chunks. Okay. And begin to send, also at a high rate, back to Alice. So mutual appreciation at the end. But Alice needs to be optimistic at the beginning, right? Trying to have faith, trust that whoever receiving the data would appreciate the effort. So higher upload rate finds better trading partners. Okay? And so you get files faster this way. All right, so that was the last of BitTorrent. And finally, we run into the quiz number 10. So quiz number 10 here is about a BitTorrent system. You heard earlier, actually yesterday, right? So to join the torrent, a peer needs to what? Go to the tracker first to get this initial set of neighbors that you connect to. All right, so therefore you see the row of these torrents, the row of these trackers are very crucial. Right? So if we bring down all these trackers, then in a way, it's hard for new peers to join the torrent. Okay? So over the years, these trackers are actually struggling. Okay? Q1 there is to ask, why are these high-profile trackers being shut down all the time? Okay? So some organizations are constantly shooting down these trackers. So let me give you a few examples. Peers come and go, but BitTorrent trackers also come and go. Okay, so some of the very high-profile trackers are already gone, like Torrent Spy, Loki Torrent, BT Jungles. BT Junkie. Yeah. So the maintainers of these high-profile tracker sites, they gave up eventually. But there's one called Private Bay. So this one is still struggling. It was down and back and down and back and down and back. So what I'm posting there on the slide is, I think, a news back in 2016. Yeah, because Pirate Bay, the domain name, is actually registered in Sweden. Okay, and at some point, the Swedish court actually rule to seize the domain name. So that gave Pirate Bay some trouble. Even though the server is still running, but they could not be using the domain name anymore. So the DNS lookup would not work. Okay, so you see there. So the issue. it's very easy to kill a tracker, even though P2P network itself, BitTorrent, the torrent itself is resilient, all right? Because it's actually very hard to bring all the peers down, okay? As long as one of us is still standing saying, no, I want a free world where there's no hierarchy, okay? So, but trackers, okay, for a new peer to join, okay, there needs to be a tracker somewhere so that this peer can look up for a set of peers to connect as neighbors. All right, so Q1, why are these high-profile trackers being brought on? Q2, how to make the trackers hard to shut down entirely. All right, so these two are the questions. And yeah, you have 3 minutes. Okay, this one is not that hard. 3 minutes, and then type up what you think. Okay, why they are brought down and how to make them resilient. Set a timer for 3 minutes. Yeah, but Rocket, think otherwise. If you are one of these free-spirited Pirate Bay operators, how would you make sure that your tracker is resilient? Yeah, I know. Okay, I'm guessing that there are the EECS school graduates. All right, so 3 minutes up. Yeah, I do see Team 1 saying that the websites are being taken down mainly because of the content being distributed. That is very likely the chance. And And the news yesterday is that a couple NTU graduates, okay? They did not name which department. It could be CSIE, it could be EE, because we also have a CS group here. I think chances is higher that they are from the CS group, okay? I might have known them. So yeah, the real issue is that they are not openly sharing, not only openly sharing copyright protected content, but also that they're making money out of it. That's one of the reasons they are brought down, all right? Q2, yeah, so Rocket was saying that, yeah, definitely punish them hard. That would actually take down these trackers effectively, right? So being up on the news will actually bring them down and try to sort of scare people away from doing similar things. So let's see, Team 12, Q1, yeah. Yeah, they're sharing copyright contents indeed. Movie, music, software, Q2. One option is to have ISP providers to block DNS requests. Okay. Okay, so you're also thinking how to actually... Oh, okay, I see. Yeah, so you're thinking also what Rocket was thinking. Yeah, I might misinterpreted the question. Yeah, I was asking, right, if you are Pirate Bay, how would you avoid being brought down? Yeah. Constantly changing IP. Oh, a just deterministic way of changing IP. That is cool. So you have all your peers synchronized changing. Very good. That was two-way authentication. Great job, Rocket, there. Well done. All right. Okay, so Davius is there actually suggesting, that's Team 12, I think, suggesting how you avoid, right, the entire domain name being seized. Yes. Using Google DNS to avoid local regulations. Definitely. Okay. Yeah, cool. Great. And many thanks for the participations from Team 1 and Team 12. Now let's move on to the second topic. Okay, and the second topic is the second example of a P2P system. Now this one is a bit unusual. It's actually using a hybrid model. The second example, Skype. It's also working in the P2P model. The primary service is to send voice over the internet, having voice calls. It also allows text messaging and video conferencing. Right? It was quite popular back then, a decade and maybe more ago. That's before a smartphone is popular. People are still using the old cell phone to make calls. So what's nice about Skype there is it not only allow people installing the Skype software to call each other on top of PC. It also allow PC talking to regular phones and back. So you can imagine business people love the idea. They get to save a lot of international call money as long as one end is sitting on a PC. But recent years we are all using smartphones, so it's not it's not that big a deal. Okay, everyone can install an app and use either Wi-Fi or the data part of the 4G to send voice. The application layer protocol running in Skype is proprietary, meaning it's a commercial secret. The reason that we can talk about Skype here is because there are some hackers, okay, probing the nodes, intercepting messages, so we get to see a little bit how Skype works. And therefore, we see Skype network is actually hierarchical. So Skype P2P network or Skype overlay network is hierarchical. Let me explain a little bit about this term overlay network. If you think of these peer processes running on the internet, think of each one of them being a node, and the peer processes that are connected to each other having a link between the nodes. Then this Skype network, right, is also a network. It's just that it's at the application layer and overlaying the physical internet network. So that's why P2P network is also called the overlay network. In fact, it was called the overlay network first academically, and then the commercial world adapts an easier to understand term, the P2P network. And the hierarchy of the Skype network looks like this. At the lower level, once you've installed the Skype software, then you become one of these Skype clients, SCs. And some of us over time might be elected as a supernode, SN. Okay, so supernode is just like one of the peers, except that it's more resourceful. By that, Skype tried to select those who have higher uplink bandwidth, okay, or downlink bandwidth as supernode. Another important condition is this, the IP address. If the IP address the supernode is using or the client is using is global, meaning it's somewhat static and referable, destinable from other nodes, then that guy is qualified as a supernode. Okay, so supernode candidates either high uplink downlink bandwidth or having a global IP, static IP. Now, these guys, one supernode and a set of Skype clients or regular nodes, okay, ordinary nodes, form a cluster. And there could be a cluster here and there. Right. At the core, the supernodes will try to interconnect to each other and therefore connecting the clusters together. Okay, so you see, there's a core part and then there's the edge part. And the structure of the Skype network is somewhat like the internet. So at the core, it's well connected, having multiple connections to each other, but at the edge, just one connection to an access node. So this is actually Skype's network, two-level hierarchy. The last thing we talk about is this. Well, in BitTorrent, right, we talk about how one new peer joins the P2P network. Okay, so if there's a new Skype client joining, what happens is this. It's going to contact Skype's tracker, which we name the logging server. So the logging server is going to return a list of these supernodes. And this new peer will select one of these guys, usually the closest one, right? And then peer to the supernode that is the closest. And that's how a new peer joins the hierarchical overlay of Skype. Yeah, and this is the part that Polly finds the most interesting about Skype. There's a very nice trick Skype plays to get around this problem. Here. What if Bob and Alice, the two peers, are both sitting behind the NAT box, Network Address Translation Server? So if you set up a home network, and the deal with the ISP is usually that you get one IP address. But if you purchase one of these home gateways and have it running, what you might be thinking is also this, right? You can actually connect multiple devices to the home gateway, despite that the ISP provides only one IP address. Well, static or dynamic, but only one IP address. What is going on there? Well, it's going on here. Inside that gateway, part of the functionality is to do the network address translation. So all these messages coming out from the hosts behind the gateway or behind the net box, okay, within your home network, are carrying the packets using fake local IP addresses. At the box, it's translated to the IP address that ISP assigned to you. And from there, the messages can go, and the server out there can then send messages back to the IP address that the ISP assigned to you. Those local addresses that you're assigned from your home gateway is actually not reachable, okay, from other machines outside on the internet. All right, so general idea here is NAT here, although providing this, a local IP service so that you can run multiple end hosts there on the home network, but it prevents outside peers, outside hosts from initiating a direct connection to you. All right. So if Alice and Bob, the two peers, are both behind NAT, they cannot be setting up a P2P connection directly to each other. And the trick Skype plays is this, to exploit a third-party peer as a relay. So Alice and Bob here, they each have their own supernodes, isn't it? So Alice here, Alice is associated with the Alice supernode. Bob here is associated with Bob's supernode. So the both of you can pick one of the supernodes. For example, Bob picked to send voice to Alice's supernode. And the supernode here can relay the voice from Bob to Alice, and Alice sends calls back to the supernode. Supernode here relay that voice to Bob. Okay, and Bob here can establish direct connection to a node having global IP address, not behind that. Alice here has no problem setting up direct connection to the supernode, which is not behind that. Alright, so this guy here is being exploited as a relay, as an exchange point of the data voices. Alright. So each peer here initiates session with the relay, a very cute hack, and that addresses this issue that many other teleconferencing or P2P network systems back then really cool at that time. Right. Super cool, isn't it? Yeah, that's why Skype was very popular back then. It's almost like the Zoom today. But for some reason, it's losing the steam. Probably because of the sort of ad hoc best effort bandwidth it's providing. So it's definitely not overlooking the amount of bandwidth required to have teleconferencings. So WebEx, Zoom, and all these other systems these days doing teleconferencing actually have a content distribution network behind helping distributing these videos from multi-senders to multi-receivers, which is the topic coming up, streaming, and particularly streaming video. So teleconferencing system is one of these streaming services. So let's take a look at the highest level, what streaming services are. 2.6, video streaming and CDNs. Video streaming, the term is very simple. Okay, YouTube, Netflix, Hulu, and Kankan. They're all video streaming services. So what they do is essentially stream videos to you. Now, what is less heard of is this term, CDNs, content distribution networks. You probably heard me talking about these networks a little bit when I was talking about the internet structure. Right? So there's backbone of the internet, there's ISP, and there's end users. But there's also these global service providers. Content distribution network is one of these global service providers, such as Google. Right? So one of the oldest CDN company is called the Akamai. Nowadays, we do have these cloud service providers, Azure, AWS, okay, also in the market for competition to provide content distribution network services. So in a way, the video streaming services such as YouTube is actually the subscriber of the CDN services. So video streaming services high up, very close to the user, and indirect interaction with the user. The CDN is one, half layer below, although still in the application layer, but half layer below, right underneath the video streaming services. Now, in order to explain why video streaming services these days uses CDNs, I'll have to share first how hard it is to provide video streaming services. Let's look at the video traffic coming out of major services such as Netflix and YouTube. So this is according to US residential ISPs statistics. 70% of the traffic coming downlink to the household from Netflix. 60% from YouTube. So just these two video services together is already more than 50% of the downlink traffic. So you see, video, a major consumer of the internet bandwidth. And this is mainly because of the number of users we have on each of these video services and the demand. Okay, so the number is still growing, demand is also rising. So we see challenges ahead. And the first major challenge is the scale. So that is related to the demand. As the number of users increase and as the number of video demands increase. So when we have users at that scale, can you imagine serving all the videos using just one single server? If you recall, when we were talking about the hierarchy in DNS, the domain name system, we are only serving what? Host to IP mapping. That is actually very, very short messages. But now we're serving videos. Even serving short messages like what DNS is doing, we need a what? A distributed system. So you can imagine that a single mega video is not going to work. The second issue is also this. Hey, because we have so many users, and these users could be like Polly sitting right here using a desktop and connected to the wired network. But it could be, some of you guys out there, still taking the metro. You might be connected to the internet using 4G and you are moving around. So the connectivity and the internet access, you can imagine, me and a metro commuter will be very different. You cannot be sending a high quality video stream to such a user on metro and moving around. But hey, I can actually take high quality video, but send me a low quality video. Neither of us will be happy. All right, so we do have this other challenge here, heterogeneity. Different users will actually demand different qualities because we have different capabilities. Some of us are stationary, some of us are mobile. Some of us has a lot of bandwidth to download videos, but some of us don't. Right? So to address the demand, to address the heterogeneity, in these users, solution is to use CDN, which is a distributed application level infrastructure. We'll definitely talk about CDN more later. Now let's talk about the video a little bit more. This is the content we are distributing there. Originally it was an analog signal. It's a sequence of images that we are displaying. And the display is at a constant rate. That means at every time unit, you take a snapshot of what it looks like right now. So therefore, at a constant rate, a sequences of these images. So for example, we take 24 images per second. So that is what the cameras are doing, taking images continuously. Right? So Poly right now is sending 30 images per second, or sometimes it's also called 30 frames per second. Your display, will be displaying 30 images per second as well. Now, 30 images per second is actually pretty low. Therefore, from time to time, you see Poly's action is a little bit, awkward, not exactly smooth. These days, in order to make sure that you have very, very smooth motion, 60 frames per second is the way to go. Right? But hey, sending 60 images per second versus 30 images per second, that is at least twice the amount of traffic. So you see a little bit of trade-off there. If we want very high video quality, that also usually imply higher bandwidth requirement. And the digitalization process is this. So every second we take a certain number of images, and within each image, we divide the image into discrete number of these pixels. So you see each of these red dots is a pixel. Okay? And for each pixel, we use a limited number of bits to represent the color. Okay, so usually the intensity of the red color, intensity of the blue component, intensity of the green component. Now, because the number of bits is limited, so that you actually approximate, okay, the actual intensity to some quantile. So this is also called the quantization process, digitalization or quantization process. Now, coding. So provided all these bits being generated, the next thing we do is to just simply send it. Okay, how about that? Well, that was actually what we were doing maybe a couple decades ago. Okay, but nowadays we add compression mechanisms or coding mechanisms. All right, so compression, coding. Compression is more specific, meant that we would reduce the number of bits we need to transmit, reduce the number of bits we need to store for the same content. But coding usually is more general, okay, not necessarily reducing the size, sometimes increasing the size for the purpose of trying to recover from errors. Okay, so coding is a little bit more general. It's just that when we're talking about coding videos, it's usually just compressing videos. And we're exploiting, okay, redundancy that is natural in the content. So redundancy could exist here, okay, within one frame, within one image. You see here the sky, all these pixels in the sky, they would actually look very much the same. The colors are pretty much the same, right? So that is called a spatial coding. Okay, so instead of sending all the values one by one, okay, how about sending only two values? The color and the number of times the pixel, the color is going to repeat. Okay, so two numbers instead of n numbers. That reduces the number of bits we need to transmit. Okay. The other way, so that was spatial. The other way is temporal. So that is to look at this from one frame to another frame when we're in action. Okay. For most cases, so action, you will see that frame I and the next one, I plus 1, there's not going to be much difference. So, hey, these pixels remain similar here. The colors pretty much stay the same, right? So why don't we, instead of sending all the pixels in a frame, okay, send only the differences from the new frame to the old frame, right? So if we take a subtraction, okay, newer frame subtracting the older frame, then you get, very little differences. Most of the pixel differences are probably just 0. Then it's much easier to send a whole bunch of zeros, which you could use just 0 and the number of times the 0 repeated itself. So a combination of spatial and temporal redundancy exploitations. In the coding schemes, the really old one, those that are decades ago, are the constant bit rate coding. Because what? The number of bits is fixed to represent each pixel, and the number of pixels is fixed per image, and the number of images you take per second is also fixed. Therefore, the number of bits you're sending out is also fixed. Nowadays, the coding is variable bit rate. So it really depends on the amount of spatial and temporal redundancy you can exploit. Those movies with really fast actions, then you don't get very good compression rate because the diff from frame I and frame I plus 1 usually large. So you don't get to save too much. As a result, the bit stream you send out is in different bit rate. Okay, so lots of actions, high bit rate. Not much motion, low bit rate. So examples. This is MPEG version 1, MPEG version 2, MPEG version 4. And you see in the older version, the encoding rate is much higher. Okay. Nowadays, using MPEG-4, the suffix of the file names of MPEG-4 video is usually just this, MP4, something something dot MP4. Compression rate is really good, so we could send very high quality video under 1 megabits per second. Now, yeah, you see version 2 seems to be requiring more bandwidth. That's because it's in DVD quality. The number of pixels that you're sampling is way higher. Okay, so CD-ROM is actually pretty old, as I said, a decade ago, and maybe a couple decades ago. All right, so that was the basics of media streaming. Now let's move on to hear about the tricks people play sending these multimedia content. Streaming stored video. This is among the most used video streaming services in the world right now. So there's live video. There's also interactive video. Those are actually harder to do. We're not going to talk about those services. If you're curious, please feel free to dig into Chapter 7 in the textbook. But as an introduction in Chapter 2, we just talk about this one here, the stored video. This is also the video on-demand service that Polly mentioned slightly earlier. The service model, hey, surprise, surprise, client-server based. So the server being where the videos are stored, okay, and the client is the consumer of the video. Okay, quite straightforward. And streaming is just to pull the video frames one by one across time. And the first protocol that I'll be introducing is called the DASH, Dynamic Adaptive Streaming over HTTP. So from here, you see that this is what video streaming over HTTP and over, therefore, TCP. So unlike what we have expected probably, right? Video services does have high bandwidth requirement and short delay requirement. But TCP, how would it serve? Okay, well, for video streaming services. Well, the main reason will be explained the next topic called CDN. Here, what we are addressing is this. Between the client and the server, there's the internet. Okay, internet fluctuates a lot if you think about it, right? People come and go, sending other video traffic, sending other big file download traffic. Now these is gonna, interact with each other, and therefore the available bandwidth really between the client and the server is varying a lot over time. So Dash here is to try to adapt, okay, to the internet conditions. That is very dynamic. All right. So the main intelligence is actually at the client side. Okay. What server did is just to prepare such that the client can be intelligent about, okay, about streaming video over the internet. So what the server is preparing is doing this. Video files are usually large, and it's usually many frames being played or being transmitted over time. And so what the server did first is to divide the video files into shorter segments. Okay. So here in the slide, we call it chunks, video chunks. A little bit like in P2P, BitTorrent actually cut big files into what? Chunks. And each chunk is stored and encoded in different rates. If you recall when we were talking about videos, right? Depending on how much detail you want to keep in the video, depending on the quality of the video you want to be able to play back. You might want to encode it at different rates. Okay? Higher rate usually meant that more detail, better quality. Lower rate usually meant less detail, lower quality. But the trade-off is, hey, for high quality video, you do need a bit more network bandwidth to transmit. But for lower rate video streams, there's less need of bandwidth. Okay, chances higher that you don't run into trouble sending a low-rate video stream over the internet, right? So, well, to allow these, flexibility, okay, depending on how the client senses what the current network bandwidth is, The server is actually storing each chunk and encoding multiple versions of these chunks at different rates. So when the when the network bandwidth is good, then we could download a higher quality video, a higher rate video. When the network bandwidth is not sufficient, we'll have to drop to a lower rate, version of a chunk. Now, what's being communicated to the client from the server is this, the manifest file, which is providing the location, the address of all these different chunks at different rates. All right. Now, the client. What the client does is periodically measure the client to server or server to client bandwidth. Okay, so what it means here is exactly the available bandwidth. All right. And then, provided this bandwidth limit, consult with the manifest file and then request the chunk the client is looking for at the time and chooses the maximum rate such that it's under the bandwidth limit. Okay, so measure periodically the available bandwidth, pick the version of the chunk such that the rate is right below the limit. Okay. And at different point in time, so periodically, the client does the measurement of the available bandwidth. If it gets back up again, then you pick a rate that's a little bit better. Okay. Otherwise, if the available bandwidth drops, pick the rate that is a little bit lower. All right. So you choose different coding rate depending on what the available bandwidth is at the given point in time. Right. So you heard that the client is actually pretty busy. It's measuring the available bandwidth and deciding what is the best rate of the chunk to download. So bandwidth, higher rate, or lower rate. So this is one of the intelligence, the dash client exercises. There are actually two more intelligences that are implemented in the client. The second one is this, where to request the chunk. And the third, when to request the chunk. Let's talk about each of these a bit further next. Where to request the chunk. What happened there is that in the manifest, there could be multiple URLs indicating that there are multiple servers carrying that particular chunk at that particular rate the client is looking for. Now, among many of these physical servers offering the same chunk, same rate, the client needs to pick one of these. Okay, so the typical decision is to pick the server that is the closest to the client. By closest, usually people mean the server that is showing the smallest delay back to the client. Now, how do you get the delay from the client to the server and back? Well, the client can send a short ping message, and see how long does it take for the server to answer back, or to send trace route, for example. So clients are also, in the meantime, sending these probes to find out which of these servers will be closer to the client. And this is also done periodically, just like how the network bandwidth is measured. All right, so that's all for the first hour of the lecture today. There are a few questions showing up. So let's go over them. So Rocket was asking, let's see. Yeah, are all our packets sent serially? They are being sent out serially from the sender, and they need to be played back serially at the receiver. But as they travel through the internet, they might get reordered. So don't worry, later on I'm going to talk about there's going to be a receiver buffer at the client side, at the playback, the player side. So you get to reorder the packet back in series. So that's going to come up in the next video. Now the next question. Okay. Are audios included in the entire stream? Yes, they are. They are part of the entire MPEG-4 stream. So they are not sent separately. And RNG was asking, yeah, if the video is said that it's just a whole bunch of still images, would it be uploaded faster? Yes, they will be, because there will be less bits required to encode it. Therefore, they will arrive a bit faster. All right. Is video less than 1 megabit per second being good, and about what resolution? It really depends on how much motion there is in the video. But roughly speaking, that's about 720p. But some 720p might go beyond 1 megabits per second. So yeah, it's a little bit hard to say, but I think about that range. All right, let's see what else. Yeah, I think that's all. And let's take a break for 10 minutes. If you have other questions, feel free to type it up on live chat. We'll come back in 10 minutes. And just like I did earlier, I would try to restart the OBS so that I don't, see crashes in the middle of the lecture. All right, so let's take breaks. All right, so let's continue with Dash. When to request the chunk. This is actually the intelligence that is a little bit hard to explain because we did not talk about a very special component in a streaming system. So let's go back a little bit to the architecture. So there's the client side and the server side. At the server here, we have huge hard disks storing video chunks and allowing clients worldwide to pull the video streams down to the internet. First component these video frames hit is the socket, okay, at the client. But then quickly, it enters this thing called the video buffer, okay, or the client-side buffer. So video frames we're getting here first. So the app that the users are playing with is more graphical, okay, and where you see a play button like this. Okay, when we hit play, what happened there is that the client sends a short message to the server that, hey, I'm gonna download this video at this rate, okay, and video frames begin flowing in. All right, so you can think of the buffer like a bucket, and if you think of these video frames as a flow of water, then it will be easier to understand. All right. So usually what happens is here, the client, before we really play back the videos, we keep a number of these frames first. Okay, when there is enough of these, so it's like a reservoir here, the buffer. Okay. Then we begin to pull the frames one by one and then render it on the player. Okay, so the time you hit the play button until the time the first frame begins playing, that is called the buffering delay, okay, or the startup delay of these stored video streaming services. All right. Now, the reason that we actually store a number of these frames before playing back is exactly because of this. Usually the playback rate is constant. So for example, 60 frames per second. So this is usually to ensure a smooth experience, right? So viewers will all prefer a higher frame rate if possible. Okay. Now let's say that, hey, we're going for 60 frames per second rate, but the network bandwidth here suddenly goes really bad. Okay. What's occurring here at the buffer space is this. Well, we are fetching still 1 frame per second. Okay, 60 frames per second. That is, so 1 frame per 1/60th of a second. But the thing is that the network bandwidth goes down. The incoming rate of the frames will be much lower, and it will not take much time until what? We see the buffer space emptied up real quick, and eventually there's no more frame in the buffer. Okay, that is called the buffer starvation. The buffer is starving of the video frames. Is that good? It's actually not good. What happens here is you're seeing your screen smoothly playing video frames one by one, but suddenly what? It freezes. Okay, so that is called an interruption. So that's very disturbing to the viewing experience. Not good. So the client usually sends back another message to the server saying that, hey, you know what? The network situation is not good. How about that I download another version of the video such that the rate is lower? Okay, I'm okay with the lower quality because otherwise I will not be able to sustain the frame rate I was looking for. Okay, so usually you'll be automatically switched down to a lower resolution, okay, or a lower frame rate, for example, just to ensure smooth playing back of the video frames. Okay, so when to request chunks so that the buffer starvation does not occur. Right? And let me make sure this is clear. Right? So that message from the client to the server asking video chunks being sent with the lower rate version, that should occur before actual starvation occurred. Now, as to how much earlier, that is the intelligence the client needs to decide. Right? So Dash allows the client to implement different strategies to decide when to start changing the rate, okay, automatically according to the network bandwidth to avoid buffer starvation. All right, so it's actually the same the other way around. For the overflow situation, if the incoming rate is high and the playback rate is low, then you have what? The buffer overflow. And subsequent frames coming in will get dropped, just like you see packet drops inside the router. Okay, so this can happen when you hit pause, okay, on your player, right? Because then you're not playing any frames out, and yet the buffer gets filled and filled and filled. At that time, the client is going to send back a message to the server and asking, oh, stop streaming. Okay, stop streaming. So that is to avoid overflowing. And your client is there also trying to do some intelligence there, okay, to pre-stop the coming in of the frames. All right, so that was Dash. And we did have a question from Kevin. Yeah, so what if we find for the same chunk, there are other copies of it or other versions of it somewhere among the servers? Do we re-download the better version? Usually in a streaming application, especially video streaming, bandwidth is very scarce. So we don't usually re-download chunks, but we might switch, okay, to fetch video from another server if the server provides better, okay? But that would happen slightly later, all right? Good, so let's move on to yet another very important design component for streaming services, the CDN. CDNs, Content Distribution Networks. This is the part in video streaming services Poly finds the most amusing. Some of you might know, many of the global services that are popular worldwide uses some sort of CDN in the back. So that includes Gmail, Dropbox, even the Zoom teleconferencing system that is a bit controversial these days. The reason for that is this. You hear a little bit back, Dash. Okay, so Dash there is nice. The client can actually adapt. Given this much network resource, we ask for the video chunks and the version that's just behind, okay, just below the available bandwidth. Okay, so this adapts to fluctuations on the internet, which includes when the number of users increases, yeah, the remaining available bandwidth will be lower and lower. But Dash there does is just to adapt to the change. The thing is that the change could become unbearable. So if the number of users increase continuously, okay, and if a high number of them are demanding the service simultaneously, you could end up with available bandwidth that is so low, it's not even sufficient to serve the chunk with the minimum rate. And to deal with the network capacity issue is what CDN here is mainly to address for. Again, there's a critical issue on popular systems on the internet today, the scalability issue. Okay. And CDN here magically addresses some aspects of these scalability issues. Let's step back a little bit and look at option 1. So this is to contrast CDN. And this is the simple, naive solution. What about using just one server? Yeah. If you recall when we were discussing DNS system, the name IP address mapping service, we were saying that originally there's only one server instead of having a distributed service, isn't it? Yeah, using one server, we have what? Issue, like this, single point of failure. That server down, the entire service down. The mega server down, the video streaming service is also down. And that one server there is also the point of congestion because everyone is asking for its service. And they'll be part of the world being happy because they are close to the server. But there will be the rest of the world will be unhappy because they are farther away from the server. And delay long is not good. And there's also a fairness issue, isn't it? How come you always get to enjoy short delay service, and how come, okay, I always have to wait? And last, this one is more distinctive in video streaming service. In DNS, the name to IP mapping are all short messages. But here, for video streaming, it's continuous, and each frame is already bigger than the name IP mapping. So we're sending these streams repeatedly, and some of the streams are probably the same. So users might be requesting popular videos, which means we are sending multiple copies of the same video over and over again. Right? Now, not a very thrifty way of using the network resource. Okay. Solution like this, definitely not scale. This is very clear. And that takes us to option 2, which is exactly what CDN is doing. That's, instead of using just one physical machine storing one copy of these content, let's use multiple machines storing multiple copies of these content. And more importantly, okay, distribute them around the internet, making sure that they are very widespread geographically. And the point of doing this is so that, hey, if there's a server here, the clients around it will be able to communicate and get the content within the local area. Therefore, the network capacity, other than this part, can be opened up for other clients interacting with other servers. Okay, so the number of duplicate video transmission can be reduced. A more efficient way, a more thrifty way of utilizing the network resource. Now, let's talk about the two models the CDNs are architecting their physical infrastructure. First one is called the enter-deep. Okay, so this is actually speaking that the infrastructure, the machines themselves, okay, for storing these videos are actually deep, closer to the end customers, deep into the ISPs, to the local ISPs, so that they are close to the end customers. Akamai, one of the oldest companies, is implementing exactly this architecture. Therefore, there are so many locations around, okay, in Akamai. Pretty much for each local ISP, Akamai probably set up a site where you see typically a rack of workstations, and there are redundantly connected to other machines in the access network, other routers in the access network, and potentially very close to the users. So Akamai there, when they deal with an ISP, they rent for the rack space, they rent sometimes for physical machines on the rack. They definitely subscribe to the connectivities provided by the local area access networks. Now, the other model is bring home model. Okay, so by bring home, these CDN architecture is to say that the physical infrastructure, the servers, okay, they're storing video contents, are actually closer to the service home, where the origin of the video sources are from. Essentially, the company generating the video. Right? So it's actually closer to the home company. Therefore, they are actually higher up in the internet hierarchy, closer to the core instead of to the local access network. Okay, so they are actually very close to these POPs, the internet exchange points. So the idea is that such a CDN company will build up a few racks of these workstations and just connect to the POPs where they get access to the rest of the internet. Right? Now, because the number of locations is very limited as the number of POPs are also limited, so there are not many of these sites. And the sites tend to be bigger. Instead of calling them sites, they are called clusters. Okay, so the physical infrastructures will be formed by server clusters. Okay, few of these clusters are interconnected through the POPs, the Internet Exchange Points. So they did not go deep into the access networks. Limelight, this is a cheaper CDN service, offers bring home CDNs. Now, so you see a little bit also advantages and disadvantages of the two models. This closer to the end customer, some big wealthy service providers might subscribe to this because potentially maintaining the infrastructure is very high cost. Now, those smaller service or smaller content providers, not quite as wealthy, then might subscribe to a bring home CDN service. All right, how do you find CDN? As amused as Polly is, isn't it? Now let's take a look at a couple examples of the CDNs. And let me illustrate how the content consumer or the client, content provider, the origin server, as well as the CDN. Okay, CDN is the one distributing the content, how the three components interact. And I'm going to use Netflix as an example. All right, so client here will be retrieving a video, and origin server here, the content provider, Netflix over here. So CDNs, the content distribution network that Netflix subscribes to, will be allocating a number of physical machines worldwide, okay, and stores copies of the content. All right, good. Okay, so the motion is this. Okay, a user, a customer turned up, okay, and decided to watch Mammoth, the movie. Okay, so the user here is obviously a subscriber of Netflix, then it would send the request to Netflix. And Netflix would then send back a manifest file telling the subscriber where the copy of the video is stored. So this guy, this guy, this guy, this, all 7 of them will be reported to the client, to the subscriber. And subscriber then will pick one of them. Okay, so redirected to the nearby CDN to retrieve the content. Now what's nice about having CDN is not just the content therefore is closer to the client. It's also to address this issue. If the network goes bad here, okay, from the first CDN, the client there can choose a different CDN where the network congestion is lighter and go this way. And CDN working this way is also called a over-the-top service. Allow me to explain. And it's better explained illustrating it this way. So let's bring all these entities involved in a CDN service high up, like this. Okay, so you see there's a separation of the internet physical structure and the OTT service. So these CDN servers, as well as the original server, as well as the client, they form a network. It's a service network. It's a network formed by what? Hosts only. Now let's abstract away the infrastructure here using just a channel. Okay, so you see here, high up, this is a network. And CDN, you can think of it as a service provided to the content provider such that we enable end-to-end or host-to-host communication. So it works like there's a network at the application layer. Now, maintaining such a network such that it works very efficiently distributing content is not easy. There are a lot of key design challenges. Okay, one is, hey, as we mentioned earlier in the example, right? The client will then select a nearby CDN node to retrieve the content. Okay, that is usually because the delay will be shorter, and the segment of internet involving the communication is short as well. Therefore, less chance of other traffic interfering with this one. But how do you know a shorter delay one is certainly the one that uses the shortest segment to travel? How? And maybe you want to use a combination of short segment and short delay. So, yeah, exactly how you design selecting of the CDN node, that selection algorithm, that is something to be investigated about. Okay. Second, in the presence of congestion, well, congestion comes in, very light level, sometimes very heavy level. Would viewers be really unhappy about a certain level of congestion? It might really depend. Okay, so how do you know when to switch from one CDN node to another one? Yeah, that is another challenge. Okay, so one could come up with algorithms that switch ahead of time before it goes really bad, or switch right at the point that's needed. Okay, you see that each of these strategies may carry certain advantages and disadvantages over one another. And last, wow, at the beginning, right, we said that CDN would choose a number of physical machines and maintain duplicate copies of a certain video. But which machine? And which video? Yeah. So this really has a lot to do with resource allocation and where the demands are. You want to make sure that the content is pushed closer to the demand, but you cannot be copying all the content, right, to every CDN node. So how do you conserve? Again, challenging problem. If you're curious, definitely read more into chapter 7. Okay, what's remaining are just 2 examples of how CDN requests are being redirected such that it reaches the physical location. So in the first example, it's more the Akamai model, which borrows from the services provided by DNS. So example goes like this. Bob requests a video from cinema.com, and this is the video ID. Okay, so browser here, browse around and decided, and Bob here hits this link. But the thing is that that video is actually stored here physically. The King CDN, a CDN company. And so it's stored on kingcdn.com's web servers, this location. But what happens here is, well, Bob's browser actually sees this is the host to contact. So first thing first, ask the local DNS server for the IP address of this guy. Right? So resolve this guy. Bob's DNS server there will what? Check cache. If not a hit, go to the TLD server. TLD server will share what is netcinema.com's authoritative DNS server. And so Bob can direct the query to the authoritative DNS server for the IP addresses of netcinema.com. But what's really curious here is the authoritative DNS server of netcinema.com, instead of returning an IP address, it returns the redirected path. Okay. At this point, Bob's local DNS then resolve for this name instead. Okay. And so check the cache, check with the TLD server, and eventually reaching the King CDN's authoritative DNS server. That query goes, and finally now, King CDN authoritative DNS server will return the IP address of kingcdn.com. Okay, so IP address of this guy acquired, and step 5 sends that IP address back to Bob's web browser. From there, Bob's browser can fetch the video from the actual location of the video. Right? So this is redirecting the client to the copy through the DNS service. In example 2, the content provider here only needs to do the minimum, which is to provide the logging service. So Bob here as a subscriber just logging first. Okay, that's step 1. And quickly, Bob is redirected to the CDN. And in Netflix's case, Amazon's cloud is the CDN. So Bob here will be browsing what videos there are available, okay, and ratings and how long the videos are from the web servers Amazon has already set up. Now, once Bob has decided on watching a video, then step 3, the manifest file of that video is returned back to Bob. And Bob will begin to fetch the video from the physical machine Amazon has set up to store that particular video, and somewhat close to Bob. Last is just that the CDN server begin to dash over HTTP streaming the video. Now if we compare the two models a little bit more, we see that in the first model, the content provider has slightly better control of where the redirections should go. But in the second case, the redirection is all done by Amazon. So there's not much Netflix needs to do, or not much Netflix can do. So it's more a trade-off between control and work. Okay? So more control, more work, less control, but less work. So, well, as a content provider, you'll have to decide for yourself. All right, so that was CDN. And we're done with streaming pretty much. And the rest of the lecture is going to be PA6, the walkthrough. Now it's going to be about 21 minutes, should be sufficient amount of time to end up by I think 12:10. So, but if you have other things better to do, feel free to just leave. I think only the first part of the video is a bit more critical. So we'll take a pause at the end of the first part. That is about 10 minutes. In PA6, we'll extend PA5 a little further. Now think back. What PA5 does is to do this. File upload and one at a time, although it's in already an infinite loop. Okay, so we need to take one request, upload the entire file, and then take the second request, upload the entire file. So this service model is called the sequential service model. Okay. If you think about it further, for the second request, it needs to wait for the entire file upload for the first request to complete in order to begin. Consider the scenario where the file upload time is super long. A video file, for example. And if we have a lot of these requests coming in within a short range of time, then those who come in slightly later than the others, well, they will have to wait until all these video file uploads complete before it gets served. So those wait time could be sometimes unbearably long. Okay. This is also why when you go to certain web services, and it seems to take you forever to get the server to respond at all. Chances high that the server is also implementing the service in a sequential way. Not a very good user experience, is it? So we'll try to exploit a special functionality in Golang called the Go routine, and I'll explain right now. And the Go routine works this way. In your program, you can specify a block of code that runs in this concurrent execution mode. Right? So to be exact, you start a program and it's going to start from the first line and on and on and on. As soon as it hits the code block being concurrent, the process is going to be forked out, okay, of the main process, creating a child process. And that process is going to, starting from the first line of the code and execute till the end of the block. The main process here will actually skip the entire block and starting from the next line out of the block and continue execution. So the main process and the child process will be seemingly running in parallel. Okay, but to be exact, it's more just concurrent processing, not parallel processing. When we say parallel processing, we actually meant more that there are two CPUs and the two processes are running on two different CPUs. So at any given point in time, you do have some computation cycles, multiple computation cycles that can do the work for multiple processes. Here in Golang, you have two processes. They seem to be working simultaneously, but they are actually taking one time slice at a time of the CPU, okay, and iterating like this. So it's not exactly parallel execution. Instead, we call this concurrent execution. And that is the magic we want to exploit implementing our file upload server. And the way we'll be exploiting Go routing is this. Provided your file upload server code, right? So you sit there and wait for a request to come in. As soon as there's a request coming in, fork out the child process, allowing the file upload going here, while the main server process will skip the file upload part and back. Now, your server in PA5 is already what? A looping server, right? So it's gonna go what? Back to wait for the next request. And as soon as it hit that there's a request coming in, you'll fork out yet another process, and the main process go back to listen to the third request. Third request's upload is gonna be what? Yet another separate process. The main process is gonna come back for the yet another request. So you see, every upload request will be what? Addressed quickly, okay? But the uploading will continue on over time. But each client will actually receive some initial feedback saying, hey, the uploading started, all right? So your users will be slightly happier seeing that, okay, I'm actually being handled, it just takes time, okay, to complete. And by exploiting Go routing this way, we managed to allow file upload requests being started earlier before all the previous file uploads are complete, right? Be careful though, the entire completion time is going to be the same because there's only one CPU that we're running the processes on. Okay, so if it takes 100 cycles to upload the file, it will remain taking 100 cycles to upload the file. All right. The only difference is that the starting time of these file upload will be slightly earlier. Okay. So in a way, using concurrent execution is a way to exploit customer psychology a little bit so that we invest the same amount of money, the system capacity remain the same, while we get slightly better user experience. Right? So here in PA6, you'll be turning the file upload part of your PA5.go concurrent. Let me repeat, your PA5 specification is this. Listen at the port assigned and wait for an upload request. Read the file size first, and then begin to read the file line by line. Prepend the line count, and output the new line to whatever.txt. Repeat step 3 and 4 until the entire file is exhausted. Send the message back telling what is the original file size and the new file size. Close the connection and go back to step 1. In PA6.go, please make the code block between step 2 and 7 a Go routine, and then add a 5-second delay between step 6 and 7 just to create some extra delay and to emulate a little bit of the processing time or file writing into database time. And here's the rest of PA6. So Polly is going to use 3 examples to show you how I turn server loop.go into a concurrent server. Now, if you recall, server loop.go in PA5 is the looping version of server 102. And server 102 there is a very simple server that takes a message and then return the size of the message. So in this set of code, example code, Polly is going to show how I turn the looping server 102 into a concurrent running server 102. In example 1, what we will do is to rewrite server loop.go such that we take the main body of it and cast that part into a function that's outside of the main procedure. All right. So start server func.go and type up the following. Okay, so the main difference is this. The main body of the server 101, take that out and cast it into this function, handle connection. So that name is just, I created randomly. So in the main procedure, you see inside the for loop, the main part of it is now replaced by just calling function handle connection. All right. Now let's give it a go. So server func will be working exactly like server loop. All right. There's not going to be any surprise. So the testing of it is just the same. One thing you need to be careful is just to change the port number so that you do not collide with other guys' port number. Now, start the server first. You see launching server and then waiting for the client. Now, start the client. Okay, you see here, client saying sending a string of 13 bytes and receiving replies from server saying that 13 bytes received. Now, on the terminal that server is running, you see after launching server ... you get hello world, printing the message received. If you run the client again, the server side you see yet another line of hello world being generated. Okay, so server func.go there. Again, no surprise, it's going to just work like the server loop and wait for the next client request, serve it, and then wait for the next one and serve it, and so on and so forth. There's really nothing new here. All the APIs are known. The only difference is just that we take that code block out of the main procedure into a separate independent function outside of the main procedure. So multiple lines represented by just one line. Now let's demo. Go run server func.go. All right, server launched, and then on the lower left terminal, let's start the client. There we go. We see here on the server side, one line, hello world is being printed. So if we start the client again, yeah, server func here behaves just like the server loop, and it goes on and on, printing hello world and sending a message back saying 13 bytes received. Okay, so that's the first part. The second and the third example is in this next video. Let's go to example number 2. It's called the simple server with time sleep. Right? So this is to make the scenario a bit more interesting by adding an extra delay. Let's make it 5 seconds into the program. So this is to emulate a little bit of the processing delay in actual servers. Okay, so let's go ahead and start. Server slow.go, a slower version of server func, so to speak. Now, everything remains the same. The only place that you need to change is inside the handle connection function. And add just this one line here at the end of it. Time sleep, parenthesis, 5 multiplied time second. Now that's execute server slow. So go run server slow. Now the way we're gonna see the server slow working is this. Run client102.go once, and no surprise, you're gonna see these 2 lines being printed, but quickly after that, run client102 again. And this time you will see first line being printed real quick, but you have to wait for about 5 seconds until you see the second line. Now think about it. Why? So all we added is just the pause time of 5 seconds at the end of the handle connection, isn't it? So now think the exchange between the client and server and the execution flow. When we run the first client102.go, server would accept the connection request and then call the handle connection. And so you see quickly the server replies 13 bytes received. But at that point in time, the server goes into what? The sleep. So 5 seconds of sleep. while we here quickly call client 102 again. And that request is going to come to the server. But you know what? The server is still sleeping. All right? And it's not being able to answer the second request. And therefore, the client there prints, okay, send a string of 13 bytes real quick because client would just print that at the time it's sending the request, sending the message. But the server there is not quite yet able to reply because it's still pausing for the first request. So first request, we need to wait until the pause time expires and handle connection finishes and go back to the end of the loop and then back to the top of the loop. At that point, the request from the client is the second request from the client is finally accepted, and then you get server replies 13 bytes received. But right there, server is entering the pause for the second time again. That's demo exactly what we were describing earlier. So go run server slow.go. Okay, server launched. Now let's run the first 102 and see. And quickly run it again. You see, first line shows real quick, but the second line gets a bit of a pause before it shows. Okay, let's do it again. First one. Second one prints the first line, but wait until the second. All right, so. Oh, and by the way, you are seeing here that I seem to pop up the same line quickly, one line after another. What I did is just simply hitting the up direction arrow. Okay, so that is in Unix command to repeat the previous command. Now, let's walk through the code. Yeah, so there are actually another line being added, that is to import the time package. So allow me to scroll back up here. Yeah, package main as usual, we import these three packages. So we've seen this multiple times, but we're adding one more import here, the time package. And that's because the extra line we're adding there, using the time sleep API and using this special system variable time.second to specify the duration of sleep are both defining the time package. All right, so time sleep, very intuitively, what it does is to enforce the program to sleep for some time. And inside the bracket, you specify the duration of the sleep. And we want it to sleep 5 seconds, so we say 5 multiply time.second. If we want it to sleep for 5 minutes, then we say 5 multiply time.minutes. All right. So what's happening there is that the first call of client 102 takes the server into the 5-second wait. Therefore, as soon as we fire the second call, the net dial there from client 102 cannot be reaching the ln.accept yet because of the 5-second wait started by the first call. All right, so until that first call's 5-second wait ends, then the next dial finally meets ln accept. Okay, and then start the second upload. And now the last example. It's the simple server with Go. All right, so finally we are now doing the concurrency. Okay. So let's go ahead and start server conc.go. Okay. And all we need to do here is to prepend Go here to the handle connection function call in the for loop. So this is changing the main file. Okay, so provided the server slow.go, change now the main function and change this particular line. It was originally just handle connection parenthesis CONN. Okay, now prepend GO there before the function call. To test it out, again, run server conc. First execution of 102 should see this, and run the second time real quick, just like we did for the server slow. What's magical is this. There's no longer the need to wait. So both of these lines that are supposed to be printed by client 102 printed out real quick. There's no wait. Now demo. So let me start the concurrent version of it. Okay, server launched. So we'll execute client 102 once, real quick, and repeat real quick. And no matter how many times you do it, second line's always showed up as quick as the first line. There's pretty much no wait from the client side. You get the initial responses of receiving a certain size of message real quick, while the server side is doing the sleep, emulating, writing back to the database somewhere. Now let's walk through the code. Yeah, the only API being new is just the go, okay, in front of handle connection. What it does is to allow multiple instances of handle connection to run concurrently. Yeah. So when the first go run client102.go is fired, the server invokes a separate process to execute whatever that's in the handle connection. In the meantime, the main process of the server goes back to the top of the for loop, and therefore ln accept can be fired again when the second request comes. So dial meets accept and goes on and call handle connection once again, which goes on concurrently with the main process, meaning the server's main process goes back and being ready for the next request. Okay. So to some degree, the 5-second wait at the end of handle connection there emulates a server processing time, or some processes related to writing data back to a remote database. So the processing will still occur. Okay, it's not like magic. Suddenly the processor is working super fast. No. Okay, the CPU is just the same. All right. It's just that the server is still doing all these things. It's quietly in the background, and the client doesn't need to know. So this way, client gets initial response back real quick. Okay, and this appears that there's no wait. So the overall completion time remained the same, but users happier. The last bit is just to test your PA6.go once you've completed. Yeah, it's just very much like how you test PA5.go. Or PA4.go. Use your PA3.go and make sure that you change the IP address so that it goes to the computer that you're running your PA6.go on. All right, demoing PA6.go. So let's exit the server conc and start PA6.go. All right, so yep, and I am supposed to run PA3, yep, and see. All right, input file, let's send client 102. All right, working smoothly. Now, in order to do very quick calling of PA311999, I have to use the up arrow to restart the comment quickly. But I also have to copy client102.go so that I can paste real quickly. Okay, so do it again. Yeah, there. Yeah, printing of the lines coming from the server is just as fast as the line printed by the client before sending. There we go. Oh, there's no wait pretty much from the client's point of view. But here, server is still busy trying to finish all the processes. But that doesn't need to be known by the client. All right. So that's all. Okay. I'm just going to leave the stream run for just a few more minutes. So in case you joined the lecture late today and you wish to type up your solutions to quiz 10, here's your chance. Otherwise, many thanks for the participation. Okay, yeah, go get lunch. Okay, time to end the stream. All right, I'll see you next week. Oh, 4 remaining. Cool.